Hello students, welcome to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. So yes, we have already completed physical chemistry in this series and we have already started D&F block, but today is going to be the most important video of this whole series, I can say, because we are going to cover a very important topic, that is general properties of transition elements. So if you know that we have so many properties to be discussed, there are almost 14 properties that we are going to cover in this particular lecture. I want all of you, please sit with the notebook, write down each and every property, the exceptions, the trend along the period, down the group, everything. If you watch this complete video, I can assure you that all the trends will be very clear to you and you can answer any question that is asked from this particular concepts. Okay, so yes, this is very important video and I have personalized all these trends in a very easy and a very simplified manner so that all of you can understand. I know this part, studying from NCERT book, is difficult because it has a lot of data, lot of tables, lot of graphs, but I can assure you, you please watch this complete video and then you can tell me whether you are clear with all the trends or not. Every reason I will explain, every exception I will explain, and we are going to discuss trends very thoroughly. Okay, so yes, one more request from my side, please join our WhatsApp channel. This is very important because all the notes, the question papers, the solutions, everything will be provided in this particular channel, in this particular WhatsApp channel. Okay, so please do not forget to join WhatsApp channel. The link of the WhatsApp channel will be there in the description section of this video. Okay, so yes, now it is going to be very important video. I want all of you to sit with the notebook and let's get started. Okay, so as I told you, the division of this chapter, how are we going to cover it? So there's a small change here. So first of all, in my first part, I told that we'll be making only 3 parts, but then later I thought it can be easier if we make it in 4 parts, right? So that is why I made it 4 parts now. In part 1, we have already covered position and electronic configuration. In part 2, we are going to cover general properties. Okay. In part 3, we are going to cover important compounds. In part 5, we are going to cover lanthanides and actinoids. Okay, here another small topic is there, that is oxo anions, and we have also oxides. Okay, so I have also covered this part under this topic. Okay, so yes, now let's get started. Year wise weightage, you have already discussed 2 to 3 questions you can expect from this particular chapter, and it is very easy to score this 2 to 3 because questions are asked from certain sections and very easy questions have been asked from this particular chapter. Okay, so yes, now coming to the trends part 2. There are, as I told you, 14 trends that we are going to discuss. The first one is physical properties, second one is enthalpy of atomization, third one atomic radius, fourth one ionization enthalpy, fifth one oxidation states, sixth trend in M2 plus to M reduction potential, seventh trends in M plus 3 to M plus 2 reduction potential, then higher oxidation states, magnetic properties, colored compounds, complex compounds, catalytic properties, and then interstitial compounds, then alloy formation. Okay, so yes, now let us start with this 14 properties, starting from the first one, that is physical properties. Now physical properties, there is nothing much to discuss. These transition metals behave as metals. Okay, why we call them metals, transition metals? Because they have certain properties of metals. What are these metallic properties they have? High tensile strength, ductility. So you might be knowing what is ductility. Ductility means converting metals into thin wires. So you might have seen copper wires, right? Copper wires, everybody would have seen it. So this process of this property of metals to be converted into thin wires is called as ductility. Then we have malleability. Malleability means metals can be converted into thin sheets. Okay. Next, high thermal and electrical conductivity, metallic luster is there, very hard. These transition elements are very hard. Okay, now what is the reason for this? The reason for this hardness is metallic bonding. Okay, metallic bonding. Okay, now so here also there is an exception, that is zinc, cadmium and mercury are not very hard molecules. Okay, now what is the reason for this one? They do not have no metallic bonding. we will discuss this in detail. Okay, note down the exceptions. Okay, note down the exceptions. Now, what is metallic bonding? Metallic bonding is the bond present between the atoms of a metal. Okay, now what affects metallic bonding? Metallic bonding is affected by number of unpaired electrons. Now, if you know zinc, cadmium and mercury, right? Zinc, cadmium and mercury, these are what? These are having fully filled d orbitals, right? Their d orbitals are completely filled. Now, if the d orbitals are completely filled, then what will happen? Then they cannot take part in the metallic bonding, because metallic bonding depends on unpaired electrons. Now, because these metals do not have any unpaired electron, they are having only completely filled electrons. That is why they do not take part in metallic bonding, and that is why they are soft in nature. Next, high melting point and boiling point due to metallic bonding. Okay, again here there is an exception, manganese and technetium. Now, manganese and technetium have unpaired electrons, okay, but still they have low melting point. That is because they are stable D5 configuration. Okay, so now you can see the stable electronic configuration of manganese and technetium means that electrons are less delocalized, so that they cannot move freely in the electron sea to contribute to a strong metallic bond. So nothing much complicated here. When they have a stable electronic configuration of D5, they are more attracted towards the nucleus. So nucleus doesn't allow these D5 electrons to participate in the metallic bonding. Because they do not participate in metallic bonding, the intermolecular forces is less, melting point and boiling point also decreases. Clear? Okay, so now moving here, so we can understand from the graph. Okay, so the melting points and boiling point I'll explain little bit in detail. So you can see, as I told you, the melting point and boiling point, see, melting point depends on metallic bonding, okay, and metallic bonding depends on number of unpaired electrons. Okay, number of unpaired electrons. Now, if you see in this particular group, okay, scandium, titanium, vanadium, in this series, you see the number of unpaired electrons. In scandium there is 1 electron, okay, then in titanium there are 2, in vanadium 3, chromium 5, right? So number of unpaired electrons are increasing, metallic bonding will increase. That is why the melting point was increasing up to chromium. Now, manganese, there is a dip. Why manganese there is a dip? As I already discussed, this is a stable D5 configuration, right? Because of this stable D5 configuration, it remains close to the nucleus. Okay, so these D5 electrons cannot participate in the metallic bonding. Okay, then again if you see iron, so I'll write here 1 unpaired electron, 2 unpaired electron, 3, then we have 5, here 5, but it is a part of D5 configuration. Okay, next we have in iron there is 4 unpaired electron, 3, 2, then 0 and then 0, right? So now what happens here, the number of unpaired electrons decreases, metallic bonding will decrease. So you can see iron, cobalt, nickel, there is a decrease in the melting point. Now copper is having much less melting point, okay, zinc is having further less. Because of D10 configurations, they do not participate in metallic bonding. Okay, now if you see here, coming to this one, okay, now if we talk about, this is 3D series, right? This is 4D series and this is 5D series. So you can see same thing happens for technetium also, its magnetic point, melting point is less. And tungsten, if you remember, this is having some speciality, that is, it is the highest element with highest melting point. Okay, clear? So the two things that you have to remember, melting point depends on metallic bonding. Metallic bonding is proportional to the number of unpaired electrons. This is the first thing. Second thing that you have to remember is manganese has an D5 stable half filled configuration, so its melting point decreases. One more thing you need to remember, that tungsten is the element with highest melting point. Okay, okay. Now let us do some question quickly. Which element has the highest melting point? Just now I told you it is tungsten. Okay. Now coming to next question, the maximum melting point of first transition series and the minimum melting point of the second transition series respectively are shown by. So if you see, third transition series is 3D, 4D and 5D, right? So 3D the maximum, the D4 chromium was having maximum, and the last one zinc will have minimum. Why? Because of no unpaired electron here, right? Now coming to 4D, technetium, zinc, cadmium. So this one will have highest in the 3D series and this one will have lowest in the 4D series. So we can have a combination of chromium and cadmium. Correct answer is option number B. Okay. Okay, now let us understand what is enthalpy of atomization. So first, to understand the trend of enthalpy of atomization, let us first try to understand what is enthalpy of atomization. Now see, suppose the atoms are there, okay, you need to give some energy to separate these atoms. To separate these atoms, that energy required is called as enthalpy of atomization. Now if I show you, see, this is suppose two atoms are combined. Now you have given some energy here, as a result of which the two atoms have separated, right? This is called as enthalpy of atomization. Next, enthalpy of atomization, I can write it as EA, okay, or you might confuse with activation energy, this one. So I will write delta H atomization, okay. This is also proportional to metallic bonding, right? And we know metallic bonding is proportional to number of unpaired electrons, okay. Now what happens along the period? If you see along the period, effective nuclear charge is increasing, right? Number of unpaired electrons first increases and then decreases. So same will happen to enthalpy of atomization also. It will first increase and then decrease. And down the group, what happens? Down the group, the metallic bonding becomes more stronger. So we can say that down the group, the enthalpy of atomization increases. Now again, there's an exception of manganese. I think now you can explain, because it is dependent on metallic bonding and manganese has a stable D5 configuration. It does not take part in metallic bonding. That is why it does not take part in metallic bonding. That is why its enthalpy of atomization will be less. Okay. Now you can see that in the graph here, right? See, it is very similar to your boiling point trend. We can say this is 3D, okay, this is 4D and this is 5D. So you can see as the number of unpaired electrons are increasing, enthalpy of atomization is increasing. Now here there is a dip, that is manganese, because it's what I can say, the metallic bonding is weak because of D5 configuration. Similarly here for technetium, and after that again as the number of unpaired electrons, it increases and then decreases, right? Now if you compare 3D, 4D and 5D, 5D have more enthalpy of atomization than 4D than 3D, right? So we'll write here 2 points. First point is enthalpy of atomization is proportional to metallic bonding, okay, proportional to metallic bonding, which is proportional to number of unpaired electrons, okay. That is the first thing. Next, I can say that 3D is having less enthalpy of atomization than 5D. 3D, 4D, 5D. This should be the order. Okay. Fine. Now let us do a question here. The transition metals exhibit higher enthalpy of atomization. Why? This is because the ability to show variable oxidation states, no. Presence of incompletely filled, no. Their ability to exist in the solid state with unpaired electrons, no. The stronger interatomic interactions arises because of having large number of unpaired electrons in their atoms. Okay. The correct answer for this question is your option number D. Okay. Next, coming to question next property, that is atomic radius. This is very, very important and very crucial to understand. So first of all, see, the atomic radius is affected by two factors. There is one factor called as effective nuclear charge and another factor is called as screening effect. Now I'll explain both the factors. Now remember, effective nuclear charge tries to decrease the size of the atomic radius, whereas screening effect tries to increase the radius of atoms or increase the size of the atoms. Now question may arise, ma'am, what is screening effect? I'll explain you. See, I'll tell you an example. Suppose you are studying in a classroom, teacher is teaching here, right? You can see what the teacher is writing and you can study well. Now what if I put a screen in between you and the teacher? There's something, a layer of screens have been put. Now tell me, will you be able to see the blackboard or the green board in the same way as you were able to see here? No, right? Because there is something, obstruction is there. This is what is called a screening effect. Now how to apply it in atom? See, now see, this is the nucleus charge, this is the nucleus, these are the outermost electrons, right? Now what happens, consider this electron. Now the nucleus, consider this electron. So now what happens, this nuclear force has to reach the valence electrons. Now when there is some electrons present between the nucleus and the last electron, then the nuclear force cannot reach the last electron, right? So what we say, these electrons which is present in between, right, they are behaving as a screen. And what are they doing? They are shielding the nuclear charge, shielding the nuclear charge. So now what will happen, the nucleus cannot pull the electrons towards itself because its force is not able to reach the last electron. If it cannot pull the electrons, then the atomic size will not decrease, right? It will and there will be repulsion between these two electrons. So as a result of which the electron the atom size tries to increase here. Clear? So that is why I told you that effective nuclear charge tries to decrease the size, whereas screening effect tries to increase the size. Once again, let us understand. When there is a nucleus, there is a valence electron, there is some electrons present in between here, okay? Electrons present here, what they will do, they will not allow the nuclear force to reach the last electron. They will create some disturbance here, they will clear some barrier here. So now these force cannot reach here, and there will also repulsions between these electrons, so as a result of which the size of the atom tries to increase here, okay? So now, both the factors are, opposing factors are working. Now what happens if you see along the period, okay, what happens along the period from scandium, titanium, vanadium, chromium, manganese, okay, when these are happening, there is like D1 electronic configuration, right? This is D1, D2, D3, D5, D5, D6, then D7, D8, D10 and then D10. Now here what happens, you see initially there are very less electrons available, right? The nucleus is there, outermost electron is there, and in between there is very less electrons, D1, D2, D3, like this, very less electrons are there. This is valence, that is 4s shell, and this is your D shell, 3d shell suppose. Now here D1 only 1 electron is present, D2 2 electrons are present, right? But as we move, when iron, cobalt, nickel comes, there are 6, 7, 8 electrons are present in between this, right? So now what happens, initially when very less electrons are present, the screening effect is not that dominant. They are not, only 1 electron is present, how much it will shield, right? So that is why we can say that initially effective nuclear charge has more power here. Effective nuclear charge is more dominant here, right? Now if effective nuclear charge is more dominant, I told you what it will do, it will try to reduce the size along the period. So along the period, first the size keeps on decreasing, okay? So from scandium to manganese, it keeps on decreasing. Now what happens, there is a state, there is a situation comes when the screening effect, okay, the number of electrons are increasing, so screening effect will increase, right? The screening effect, see, as the number of electrons is increasing, the screening effect is increasing and effective nuclear charge is decreasing. So there is a level when both these factors are almost equal to each other. One tries to increase, another tries to decrease. So at that point, what we say, the size almost remains constant. For iron, cobalt and nickel, the size almost remains constant. Now when you see copper, D10, right, there are 10 electrons in between here. So here, now there are 10 electrons, so they can shield very well the valence electrons. The shielding is very good. Now when the shielding is very good, what will happen? This force cannot reach the last electron. The force of nuclear force cannot reach the last electron. If it cannot reach the last electron, what will happen? The size will try to increase here, right? If the size tries to increase, that is why we can say copper to zinc, the size is increasing, right? So very clear. Initially, there are first, I'll tell you this whole concept in 4 points. Remember, first point, there are 2 factors which affect the size: screening effect, effective nuclear charge. Screening effect tries to increase, nuclear charge tries to decrease. First point clear. Second point, initially there are less d electrons, so screening effect is not that dominant. Effective nuclear charge is dominant, so as the number of protons are increasing, effective nuclear charge is increasing, size keeps on decreasing. Okay. Now, as the number of electrons are increasing, screening effects tries to increase slowly, right? And that is a point when both these factors are equally dominant. At that time, iron, cobalt and nickel, the size is almost similar. Okay, the last point what I want to say, when d10 electrons are there are so many electrons in between the nucleus and the 4s electrons, the shielding effect is more significant, and the shielding effect wins here, and the size increases from copper to zinc. Okay, so that you can see effective nuclear charge here, it is more dominant than screening effect. Then effective nuclear charge is equal to screening effect in this region, right? And in this region, effective nuclear charge is less dominant than screening effect. So size increases. Okay. So now let us see the graph for this. Okay, size you can see here. One second. Okay. So now you can see the trend what I discussed here, that okay. Now from scandium, if you see scandium to cobalt, right? Scandium to up to iron, I can say the size is decreasing, right? Then iron, cobalt, nickel, you can see almost a straight line, right? There is less difference. Then again copper to zinc, the size has increased. So I think this is very clear. 4 points I told you, please remember and write it down. Now let us discuss down the group what happens. Okay, so now down the group, if you see, we also know down the group what happens, new shell is getting added, so the size increases, right? So now what happens, scandium, yttrium, lanthanum, if you see in this way, scandium, yttrium and lanthanum, the size is increasing. That is very regular what happens. Now if you see here, titanium, zirconium and hafnium, the size of Zr and Hf, okay, this is almost similar, this is similar, these sizes are almost similar. Now what is the reason for this? How can the size become same when when a new shell is added? So now the reason for this is lanthanide contraction. Okay, some new term you might feel, but it is something that we need to discuss, very important topic. Okay, now see, if you see lanthanum electronic configuration, it is Xe 5d1 6s2, Xe 5d1 and then 6s2. Okay, now if you see zirconium to this electronic configuration of hafnium, Xe 5d2 6s2, there is something here, one 4f orbital has been added. Now ma'am, what is the problem if 4f orbitals are added? Now something that we need to discuss. See, suppose you are sitting in a classroom. Okay, this is a classroom. Okay, and teacher is there, board is there, and you people are sitting here. Okay, now I told you if there is a obstruction in between, like if I put some screens here, then you cannot see the what is written on the board. Now here I am telling you, I am putting two different types of screen. See, this is board, here students are sitting, and I have put a screen here. Here there is some net, there is like you can see badminton net type of screen I have put, and here I have put like wooden you can say plank is kept here, right? So that there is no, you cannot see at all from here to here. Okay, there is no visibility. Okay, there is no visibility from the other side. Now what happens, both are giving you screening effect. Which one will give you a better screening effect, where the blockage will be very good? Here the blockage will be very good, here the blockage will not be very good. So I can say that here students sitting here can easily see the board. See, if I keep here and I do not keep anything, only students are sitting, this is the best condition where students can see very easily. Now if I put a small net in between, students can see with some obstruction. If I put a wooden plank in between, students cannot see at all, right? The same thing happens here. Now see, here what happens, there is nucleus. Okay, now there is 4s electron here, and now in case of this one, this is 4f electrons are present. Now these 4f electrons are like your, you think, net. Okay, means what, they obviously they block the nuclear charge, but they are not very effective in blocking the nuclear charge. Okay, because their shape, why that is happening? Because of their diffused shape. Okay, because of their diffused shape, what happens, the nuclear charge can easily reach the last electron. not easily as come. If there is no electrons, it can reject. If there is no electron, this is the best condition. But if electrons are present in the 4f orbital, then they are very poor shielders. They do not shield or they do not block the nuclear charge effectively. So the nuclear charge can easily reach the last electron. Now if this is d or f block if this is s and p orbitals, then what if this is s and p orbitals, then they will behave like this wooden wall. They will not allow at all, or I can say very less amount can go. So if I am putting this is suppose nuclear charge, so very less amount can go to this side. But here if this is the nuclear charge, okay, then almost it will pass here. Then what will happen? The nucleus, the electron will get attracted. If the electron will get attracted, what will happen to size? The size will decrease, right? So that is why when we go from 4D to 5D series, okay, 4D to 5D series, 4f electrons are being filled. Now because these 4f electrons have very poor shielding effect, they cannot block the nuclear charge. The nuclear charge easily reaches the last electron and pulls the electron towards itself, and the size almost becomes similar to that of your 4D. Clear? So that is why we can say that the 4D and 5D elements have similar size because of lanthanide contraction. I hope this concept is clear. Okay. Now we will go to the next 3.4 concept, that is ionization enthalpy. Now here you see ionization enthalpy, if we go along the period, okay, along the period ionization enthalpy increases, right, because effective nuclear charge increases. But like as in if you see in represent like in P block, there is some exceptions to the ionization enthalpy based on the electronic configuration. Here also we have some exceptions. So generally there is an increase in ionization enthalpy along each series of the transition elements from left to right due to the increase in effective nuclear charge. So this is very general thing which we study in our P block elements also. Where is the exception here? Now if you see first second ionization enthalpy, right? Second ionization enthalpy means I have scandium plus, titanium plus, vanadium plus, then I have chromium plus, I have manganese plus, I have Fe plus, right? So along the period the ionization enthalpy should increase, right? Along the period ionization enthalpy should increase. Now if you see the electronic configuration, this is scandium is 3d1 4s2. So I have here 3d1 4s1. I removed only one electron. Here it is 3d2 4s1. Here it is 3d3 4s1. Here it is 3d5, right? And manganese, here it is 3d5 4s1, right? Now if you see, if I want to remove one electron from manganese, what I will get? Mn2 plus, right? And this Mn2 plus configuration is 3d5, which is exactly half filled and very stable, right? Very stable electronic configuration. So what happens here? Because it is very easy to get from Mn to Mn2 plus, because it is gaining stability, the ionization enthalpy from chromium to manganese, okay, it becomes less. It should if you see along the period it should increase, but the ionization energy of manganese is less than the ionization energy of chromium. Okay, that is what I have written here. Why? Because when Mn is going from Mn plus to Mn2 plus, there is D5 configuration, there is stability, the stability is increasing. So manganese will easily lose one electron to get into Mn2 plus, right? Very easily it will happen, right? So we do not have to put much energy in that. It's a very easy process. So that is why ionization enthalpy of manganese goes down. Now similarly, when you talk about the second, so this is for your second ionization enthalpy. Now when you talk about the third ionization enthalpy, if you see third ionization enthalpy, we must be removing electron from the 2 plus state, right? So after manganese there is iron. Manganese configuration is 3d5 here and Fe2 plus configuration is 3d6 here. Now to remove one electron from here, Fe2 plus, I will get Fe3 plus. Again this configuration is 3d5, which is very stable. So what happens now, from Fe2 plus to make it to Fe3 plus, to remove one electron from here, it becomes very easy. We do not have to put any much hard work here, right? Easily we can remove this electron, easily iron will give away your electron so that it can get converted to 3d5, right? So in this way I can say that here what will happen, the ionization enthalpy of iron will again drop. Okay, so that is why the ionization, so along the period if you see, ionization enthalpy of Fe2 plus should be more than manganese, but due to this electronic configuration, ionization enthalpy of Fe2 plus is less than the ionization enthalpy of Mn2 plus. Okay, so these are two exceptions I am telling you. Remember the electronic configurations. If you remember the electronic configuration, then easily you can explain all these concepts. Okay, fine. Now let us go to the, let's solve some question here. Mercury is the only metal which is liquid at 0 degrees Celsius. This is due to its, okay. So mercury, if you see, zinc, cadmium, mercury, its electronic configuration is 5d10 6s2, right? 5d10 6s2. Now what happens here? So here, due to this fully filled electronic configuration, there is no unpaired electron, right? There is no unpaired electron, and because of there is no unpaired electron, it does not participate in bonding. Okay, does not participate in bonding. There is no metallic bonding. So that is why the intermolecular forces are very weak, and mercury is found to be in the liquid state. Okay, so that is because of weak metallic bond. Why there is weak metallic bond? Because there is no unpaired electron. Okay, and it also has very high ionization energy. Now if you see, this is a completely filled d orbital, very stable electronic configuration, so removing one electron here will be very, very difficult. That is why the ionization, it has very what I can say, very stable electronic configuration and high ionization energy. Okay, so in this, because of these two reasons, it exists at liquid state. So the correct answer is option number A. Okay, now let us talk about 3.5, that is oxidation states here. So this is also very important. First statement has 3 points that you need to note down. First is, there are variable oxidation states. Every metal, not every metal, most of the metal of the transition elements show variable oxidation states, means more than one oxidation state. What is the reason for that? This is due to the participation of Ns and N-1d electrons. Okay, due to both Ns, means suppose 4s and 3d, both these orbitals participate in bond formation. Why both the orbitals participate? This is because of the comparable energy. The energy difference between N-1d and Ns is very less. Okay, the energy difference is very less, so both the electrons can participate, giving you a very like number of oxidation states. Okay, now exception here is scandium and zinc. So you can see here the number of oxidation states. Scandium only shows +3 and zinc shows only +2. Other than that, all the elements have more than one oxidation states. Okay, now coming here, one more important thing, that manganese, if you can see, has the highest number of oxidation states. Okay, now one more thing, higher oxidation states are more stable down the group. That means down the group, if you see, I have chromium, then I have molybdenum, and then we have tungsten, right? So this is 6th group, if I say +6 state. Okay, so down the group what happens, these are more stable, like molybdenum in +3 and tungsten in +6 are more stable than chromium in +6. Okay, so they are saying that higher oxidation states are more stable down the group. This is not a very important point, this is very important point. These two are very important, that these two have only one oxidation states, and the reason why they have multiple oxidation states and why all the electrons participate in bonding. So that this is important, okay, in this oxidation state. Note down this much, every question you will be able to answer. Okay, now let's solve a question here. Which of the following elements with the following orbital configurations may exhibit the largest number of oxidation states? So we have just seen that largest number of oxidation state is exhibited by manganese. Its electronic configuration is 3d5-4s2. The correct answer for this question will be option number B, right? 3d5-4s2. Okay, now coming to the 6th property, that is M2 plus to M plus reduction M2 plus to M reduction potential. Okay, so here it is very, very important to understand that, see, as we move along a period, okay, what happens? Z effective increases, right? So I can say that removal of electron, okay, removal of electron is difficult, okay, removal of electron will be difficult. So that means we can say that oxidation is difficult, because oxidation is loss of electron. So along the period what happens? Oxidation is difficult. That means I can say that reduction is somewhat easy. So now let us discuss the next property 3.6, that is M2 plus to M reduction potential. Okay, so now you see along the period what happens? Becomes less negative along the period. So what happens? As we move along the period, the E0 value becomes less negative. Okay, so along the starting of the period it is more negative, towards the end of the period it is less negative. Now what happens? See, if M to M plus conversion is easy, then E0 value will be more negative. This statement please remember. What I am saying, if M to M plus 2 plus, if this conversion is very easily we can, if easily a metal can get converted to M2 plus, very easily it can get converted, then the E0 value will be more negative. More negative means, suppose what I mean by more negative, suppose along the period, what I am saying, along the period here it is more negative, okay, and here it is less negative. That means what? Here suppose it is -5, here it will be -1. Understood? More negative means you should not think in terms of number, okay, the higher values of negative. And when it will be more negative? If M to M2 plus conversion is very easy. Okay, clear? Fine. Now we will discuss the trend. Okay, so first thing what you have to remember, 2 points that I have written here is to be understood, that along the period the E negative values become less negative. Like along starting of the period it is more negative, as you move along the period it becomes less negative. The second thing that you need to know, if a metal can easily get converted to M to M2 plus, very easily it wants, happily it gets converted, then the value will be negative. Okay, now let us see the trend here. See, titanium, I told you along the period it will become more negative, it will become less negative. So we started with -1.63, -1.18, it decreased, then -0.9. Then you see again in case of manganese, here some problem is there, it has again increased here, right? Then again here it has decreased, right? Here it is decreased. Now you will tell here also it is decreased, but what can we see? See how much it has decreased here, 1.6 to 1.18, okay. Now 1.8 to 0.9, almost by half it has decreased. Now here it has increased. If you see from here 0.9 to 0.4, again by half it has decreased. 0.4 to 0.2, again by half it has decreased. But if you see here, there is decrease of only 0.03. So something problem is also here. Now if you see here 0.34, it has increased. Positive value we are getting. Next, if you see here from -2 here also it is increased, right? So we find anomalies in the 4 cases. First -1.18, then -0.28, plus 0.34, -0.76. Do not worry, there is reason for this, explanations are there, we can understand it very easily. Just you have to remember one point, if the conversion of metal M to M2 plus is very, very easy, then the value will be negative. Okay, fine. Remember this one again, what I said, if conversion of M to M2 plus is very easy, then if conversion of M to M2 plus is very easy, then E0 value will be more negative. If the conversion of M to M2 plus is easy, then the E0 value will be very negative. Clear? Okay, now we will talk here. Manganese, see, manganese electronic, okay. Manganese electronic configuration, if you know, it is 3d5 4s2. Mn plus electronic configuration 3d5 4s1. Mn2 plus electronic configuration 3d5. Now, is there anything special about this 3d5? If you know, right? 3d5 is what? Exactly half-filled configuration. exactly half-filled configuration, very stable configuration, that in this case the M to M2 plus conversion is easy, right? Because manganese is not stable, but M2 plus is very stable because of half-filled configuration, right? So that is why what less electrons are there and they are half-filled, right? So that will what happen. In this case, metal wants to get converted to M2 plus. M to M2 plus is very easy. Now what I told you, have to remember, M to M2 plus, if it is easy, E naught value will be more negative. So that is why manganese value has become minus 1.18. The value has become more negative. Okay. Next coming to here, nickel. Now if you see in nickel, okay, there is nothing about electronic configuration, but while deciding this electrode potential, we have four factors actually plays a role. The atomization enthalpy, the first ionization enthalpy, second ionization enthalpy, and hydration enthalpy. Okay. In this case, what happens? See, this atomization enthalpy is positive. Okay. First ionization enthalpy is positive. This is also positive. Okay. But the hydration enthalpy is negative. Now what happens? For nickel especially, the hydration enthalpy is very much high. Okay. So this plus is there and this negative is there, and this value is very high. Okay. As a result of very high value of hydration enthalpy, we get minus, the electrode potential is less negative. Okay. What I am saying, let me repeat it again. Along for electrode potential, there are four factors: atomization energy, first ionization enthalpy, second ionization enthalpy, and hydration enthalpy. Now in case of nickel, what happens? The hydration enthalpy is very high. That is why the E naught value is less positive. How much less negative? How much negative we expect it to be? It is less than that because it has high hydration enthalpy. Are you getting? Let me repeat once again. Nickel, like we expect that from minus 2.8 it should almost come to minus 1 something, right? But it is more negative than what we expect. Sorry if I told, I think before I told less negative, sorry for that. What I am saying here is minus 2.8, if the regular trend is following, it should get around half of it, minus 1 something we should get. But we are getting more negative than the expected value. We are getting minus 2.5, right? And this is because of very high negative enthalpy of hydration for nickel. Okay. Now coming to copper. So I will erase this part. Sorry. Okay. So I'll erase this part. So again, this for except from nickel, other all thing is the game of electronic configuration. So if you see copper, electronic configuration is 3D10 4s1. Okay. Copper plus, it is 3D10. Copper 2 plus, it is 3D9. Right. Now where the metal is very stable, in Cu plus it was very stable, right? The first ionization enthalpy will be very low because easily metal will give this 1 electron to get converted to 3D10. But if you see Cu2 plus, will the metal to want to gets converted to M2 plus here? In manganese we say yes, but in copper it is no. Why? Because copper 2 plus is not a stable configuration, rather copper plus is a very stable configuration. So metal will come here easily, but here it will not try to come, or it doesn't want to come here. So here I told you, if the metal gets converted easily, M to M plus, the value will be very negative. If it is very difficult, then the value will be positive, and that is why we can say that copper electrode potential is 0.34. And you can also see the second ionization enthalpy of copper is very high, 1958. Due to this very high second ionization enthalpy, the overall electrode potential comes out to be positive here. Okay. Why second ionization enthalpy is very high? Because you are removing 1 electron from a very stable configuration. Okay. Now coming to zinc. Again we will explain on the basis of electronic configuration, right? So now what happens for zinc? If you see that zinc electronic configuration is, zinc electronic configuration is 3D10 4s2, right? Zn plus will have what configuration? 3D10 4s1. Zn2 plus will have 3D10 configuration, right? Now what happens here in 3D10? Is it a very stable configuration? 3D10 fully filled. Then will the metal will be easily converting from Zn to Zn2 plus? Obviously yes, right? So if the metal can easily get converted from M to M2 plus, then E naught value will be more negative, and that is why the E naught value is more negative than the expected value. Clear? I hope all these 4 exceptions are clear. First is your manganese. Manganese gets easily converted to Mn2 plus because of stable D5 configuration. That is why the E naught value has negative. Now coming to nickel. For nickel, there is no role of electronic configuration, but the hydration enthalpy is very high. That is why the value is more negative than expected. Now for copper, Cu to Cu2 plus conversion is very, very difficult. So because it is difficult, I told you if it is easy, it will be more negative. If it is difficult, it is positive. And because this is of high second ionization enthalpy. Okay. Now coming to the last one, that is zinc. Here Zn to Zn2 plus conversion also, the metal easily will get converted. So that is why the E naught value is becoming more negative here. Clear? Okay. Now coming to M plus 3 to M plus 2 reduction potential. I'll tell you this concept, this part is very, very easy if you remember that electronic configurations. If you remember the electronic configurations of these atoms, of these elements, then this part is very easy. Now, okay, I'll tell you one mantra here, okay. What you have to remember, if M plus 3 to M plus 2 conversion is easy, okay, then E naught value will be high, okay. Second thing, the opposite, if M plus 3 to M plus 2 conversion is difficult, okay, then E naught value will be low. Clear? Let us repeat it. I want everyone to repeat. Comment down, write it and repeat again and again. What I am saying, plus 3 to plus 2 conversion, if it is easily metal is going to getting converted, E naught value will be very high. Plus 3 to plus 2 conversion is very slow, okay, the metal does not want to get converted to plus 2, then E naught value will be low. Once again, plus 3 to plus 2 conversion is very easy, metal wants to go to plus 2 state from plus 3 state, then E naught value will be very high. M plus 3 to M plus 2 conversion is very slow, metal doesn't want to go, in that case the reduction potential value will be very low. Clear? Once again, plus 3 to plus 2, if it is easy, reduction potential value will be very high. Plus 3 to plus 2 is difficult, reduction potential will fall down or the value will be very less. Okay. Now let us see here. Scandium plus 3 to scandium plus 2. What is the electronic configuration? Scandium. What is the electronic configuration? 3d1 4s2. Scandium 3 plus, what it is? All the electrons will go, so noble gas configuration. Scandium plus 2 is what? 3d1. Now see, scandium plus 3 is very stable configuration. Why? Because it is a noble gas configuration, right? Then will the metal here wants to come to a unstable configuration of 3d1? Will the metal want, or it is happy in plus 3 state? Obviously it is happy in plus 3 state because it is very comfortable here because of noble gas configuration. So if does the metal wants to come, plus 3 to plus 2 will be easy here? No, right? Because plus 3 is very happy here, metal wants to be in plus 3 state, so you have to push them to come to plus 2 state, right? So that is why it is difficult here. If it is difficult, E naught value will be low. What is the reason for that? Because Sc3 plus configuration is very stable due to the noble gas configuration. Okay. Now coming to the next one, Zn plus 3 to Zn plus 2. Let us see. Zn electronic configuration is 3d10 4s2. Now if I make Zn plus 3, 3 electrons, 2 electrons will be removed here, from 1 electron will be removed from here, 3d9. Zn plus 2, 2 electrons will be removed here, so 3d10. Now can you tell something, is there anything special about 3d10? Is there anything special about 3d10? Yes, ma'am, it is fully filled configuration, very, very stable configuration, right? If it is very stable configuration, then metal will come here or not? Metal will, so you just imagine that Zn plus 3 configuration, where it is not stable, it is hut, okay, a small hut type house, and this 3d10 where it is very stable is a bungalow, right? So if you are staying in a hut and somebody tells that okay, from today you are going to stay in the bungalow, then will you run and go or not, right? So metal Zn plus 3 will easily get converted to Zn plus 2 or not, right? Easily it will get converted. If if the conversion is easy, then E0 value will be high, right? What is the reason? The stable configuration of Zn2 plus, that is D10 configuration. Now coming to next one, Mn plus 3 to Mn plus 2. Now see, what is manganese electronic configuration? 3d5 and 4s2. Mn plus 3 means what? 3 electrons you will remove, 2 electrons you will remove from here, 1 electron you will remove here, 3d4. Mn plus 2 is what? 2 electrons you will remove from here, it is 3d5, right? Now you see, this is a stable, anything special about 3d5? Yes ma'am, this is half filled configuration, again very stable configuration, right? Half filled stable configuration. In that case, will the metal come here or not? Will the conversion will be easy or not? Which is hot, which is bungalow here? Because this is not comfortable, this is hot, this is bungalow. So metal will easily come from hot to bungalow, right? It will run and come there. So that is why reduction potential, the conversion from plus 3 plus 2 plus 2 is very easy here. Reduction potential will be a very high value. What is the reason? The stability D5 configuration of Mn2 plus. Okay. Now coming to example 4. Fe plus 3 to Fe plus 2. What is the electronic configuration of Fe? 3d6, 4s2. Fe plus 3, 3 electrons you have to remove from here, 2 electrons you will remove from here, 1 electron you will remove from here, 3d5. Fe2 plus, it will be 3d6. Okay. Now if you see, plus 3 to plus 2, which is a stable configuration, 3d5 is very stable, right? Half filled, very stable. So this is bungalow. Here 3d6, unstable configuration, this is hut. Now tell me, you are staying in a very big luxurious hut, bungalow, and someone tell today you have to go to shift to the hut. Will you be easily going, or you will be sad, you will be reluctant, you will go very slowly, right? Similarly, metal was happy in this plus 5 state, D plus 3 state. Now you are taking the metal to plus 2 state, right, which is not comfortable. In that case, what will happen? The process will be very slow. If the process, or we can say it is a very difficult process. So if difficult process, or if it is difficult process, then E0 value will be low value. Again, the reason is the stability of Fe3 plus due to D5 configuration. Clear? I hope this part is very clear. Examples are clear. If the reduction, so let's again, once again let's tell the mantra. If the reduction plus 3 to plus 2 is easy, E0 value will be high. If reduction plus 3 to plus 2 is low or very difficult, the E0 value will be low. Clear? Okay. Now coming to next, that is 3.8, stability of higher oxidation states. Okay. Here also very easily simplified version we will learn. First of all, the statement is fluorine stabilizes the higher oxidation state. Now see, when metal, we just understood that metal can exist in a lot of oxidation states, right? So now, when metal can be present in a number of oxidation states, there will be some higher oxidation states, there will be some lower oxidation states. So it is found that when the metal is in the higher oxidation states, it forms bond with fluorine. Okay, it binds with fluorine. So when metal is in the higher oxidation states, it forms bond with fluorine. There is one more element, we will talk about it later. Okay. Now, why fluorine? What is so special about fluorine that metals, when they are in higher oxidation state, they only search for fluorine. Where is fluorine? They will form bond with fluorine, right? So what is speciality about fluorine? So fluorine can form higher lattice energy, and it can also give you high bond enthalpy. Okay, due to very high lattice energy and very high bond enthalpy, when the metals are in the higher oxidation state, they form bond with fluorine. Clear? Okay. Now coming to when fluorides are unstable in the lower oxidation state. So if metal is in the lower oxidation state, they don't even ask to fluorine, they don't even search for fluorine, right? They at that time form bonds with chlorine, bromine and iodine, right? When metals are in the higher oxidation state, they form fluorine plus one secret element that we'll talk about it later. And when the metal is in the lower oxidation state, it forms bond with chlorine, bromine and iodine. Okay. Now here you can see, for example, vanadium. When vanadium is in plus 2 oxidation state, with plus 5 it is forming with fluorine. But when it is in plus 2, it doesn't care about fluorine. It forms bond with chlorine, bromine and iodine. Okay. Now, if copper, if you see copper if it is in +1 state, it forms bond with chlorine, bromine and iodine. Okay, but copper has some problem. Everywhere you find copper has some or the other exceptions. In electronic configuration it has exception, in electrode potential it has exceptions, right? In this also it has some exception. Let us see what. So what it is saying that when copper is present in +1 state, it can mingle with chlorine, bromine and iodine. But when copper is present in +2 state, it forms bond only with chlorine and bromine. It doesn't make friendship with iodine. It removes iodine. Now what is the reason for that? We have to understand. First we have to understand till now what points we have discussed. When the metal is in the higher oxidation state, with whom it binds? With fluorine. When metal is in the lower oxidation state, it takes bind with chlorine, bromine and iodine. We have seen the example of vanadium. Vanadium in +2 forms with chlorine, bromine and iodine. Vanadium in +5 forms with fluorine. Now what is the reason why they choose fluorine? Because of its high lattice energy and high bond enthalpy. Clear? Now when talking about copper, copper also has +1 state and +2 state. When copper is in +1 state, it binds with chlorine, bromine and iodine. But copper, when it is in +2 state, it doesn't bind with iodine. Okay, it becomes enemy with iodine. Why? See, so that is why, because it doesn't form with Cu2 plus doesn't form bond with iodine, we cannot find CuI2. CuI2 is never formed. What is the reason for that? Cu2 plus is very clever and oxidizes I minus to I2. Okay, see, copper 2 plus was there. Okay, I minus came to make friendship with copper. Okay, to bond with copper, but copper 2 plus is very clever. What it did, it oxidizes I minus to I2. It converted I minus to I2. Okay, now this I minus is getting converted to I2, so this I minus is no more available to form bond with copper 2 plus, right? So that is why you can see a reaction here, Cu2 plus. Okay, so see, okay, so Cu2 plus 4I minus gets Cu2I2 plus I2. So you can never find copper I2. CuI2 will not form. Once again tell ma'am, we are not understanding what you are telling. Let's listen again what I am saying. Copper has two oxidation state, +1, +2. +1 is a very friendly person, reacts with bromine, chlorine as well as iodine. Copper 2 plus is little different person, reacts only with bromine and chlorine. When iodine comes, copper does not react with it. What is the reason for that? The reason for that is copper 2 plus easily oxidizes I minus to I2. Okay, now I minus is not available. I minus got converted to I2. Then how copper will form bond? So that is why copper 2 plus oxidizes I minus to I2 and itself gets converted to Cu plus. Okay, now Cu plus can form bond with I minus to give you Cu2I2. Clear? Now copper 1. Now we talked about copper 2 plus, some problem of copper 2 plus. What is the problem of copper 2 plus? It doesn't make friendship with I minus. Okay, it oxidizes I minus to I2. Now let us talk about copper 2 plus. Now if you see that copper electronic configuration is 3d10 4s2 4s1. Copper plus configuration is 3d10, right? Copper 2 plus configuration is 3d9, right? Now what happens when copper plus is there? We think that okay, this is very stable, copper plus will be very stable because of d10 configuration, but here also some problem is there with copper. Copper plus, when it is in aqueous medium, okay, it is not stable. Copper plus is stable in the gaseous medium or in the solid medium, you can say, but when you put copper plus in the aqueous medium, this, even though it is having D10 configuration, very stable configuration, but it is not stable in the aqueous medium. Immediately it undergoes disproportionation reaction and gets converted to Cu2 plus and Cu. Cu2 plus and Cu. Now why Cu2 plus? It is D9 configuration. Why is that stable? D9, this is stable because of hydration enthalpy. Hydration enthalpy of Cu2 plus. Clear? Once again tell us what about copper, what is the story of copper? Let us understand. First point is copper has two oxidation states, +1 and +2. Second point, copper plus can bind with chlorine, bromine as well as iodine. Third point, copper 2 plus binds with chlorine bromine, not with iodine. It oxidizes I minus to I2. Fourth point, Cu plus having D10 configuration. It is still unstable if you keep it in aqueous medium. It immediately undergoes disproportionation reaction and gets converted to Cu2 plus and Cu. Now why Cu2 plus is stable? Because of negative hydration enthalpy. Okay, fine. Now coming to the stability of Cu2 plus in aqueous medium rather than that of is due to much more negative hydration enthalpy of copper 2 plus. Okay, so I'll erase this one. I have written something. Yeah, clear? Okay, now going to the next one, that is oxygen. Okay, I'll tell you. I told you that when metal is in the higher oxidation state, they find fluorine. They search for fluorine and form bond with that. But there is one more secret element I told you, right? That secret element is none other than our very favorite element, that is oxygen. So when metals are in the higher oxidation state, they form bonds with two elements, that is fluorine and oxygen. Okay. So now if you see manganese, okay. So manganese, so manganese can exist in +4 state and manganese can exist in +7 state also, right? Manganese can exist in +4 state, +7, both are higher oxidation states. Now in +4 state, manganese can manage with fluorine, but when it comes to +7 state, it forms bond only with oxygen, right? Only with oxygen. Now fluorine is thinking, what is the speciality of oxygen? Why elements, when they go much more higher oxidation states, they prefer oxygen? So fluorine went and asked to oxygen that what power you have, that when metals are in the higher oxidation state, they search for you rather than me, right? Generally, if you are not available, they search for me, but if you are available, they will go with you. What is the reason for that? Then oxygen answer to fluorine is, it has the ability to form multiple bonds. Oxygen can form multiple bonds and hence can stabilize the higher oxidation states better. Okay, clear? So let us recap these all things. First thing, when the metal is in the higher oxidation state, they form bond with two elements, fluorine and oxygen. Why they choose fluorine? Because of high lattice energy, high bond enthalpy. Why they choose oxygen? Because of its ability to form multiple bonds. Clear? Second point, when metals are in the lower oxidation state, they prefer chlorine, bromine and iodine. Here copper plus is there. Copper plus, very friendly person, reacts with chlorine, bromine and iodine. Copper 2 plus, little different person, reacts only with chlorine and bromine, does not react with iodine, oxidizes I minus to I2, right? Next, coming to copper plus. Copper plus is very happy when you keep it in the solid, when you keep it in the gas medium. But when you keep copper plus in the water, even though it has D10 configuration, it is no more stable. It gets converted to Cu2 plus and Cu, called as our disproportionation reaction. Now, why Cu2 plus is stable? Because of its negative hydration enthalpy. Okay, I hope this whole thing is clear to you. Okay, okay. Now coming to the next one, some questions we can solve here. The electronic configuration of copper 2 is 3d9, whereas that of copper plus 1 is 3d10. Which of the following is correct? Cu2 is more stable. Okay, they are telling Cu2, that is 3d9 is more stable. Okay, Cu plus is less stable, that is 3d10 is less stable. Okay, okay. So here I have missed. Which of the following is correct in aqueous medium? Okay, the question is like this. Okay, now Cu plus and Cu2 plus are equally stable? No. Stability of Cu plus and Cu plus depends on the nature of the copper salt? No. Now if you know, as I told you, in the aqueous medium, Cu2 plus is more stable due to negative hydration enthalpy, right? The correct answer for this question will be option number A. Okay. Now let us discuss the next property, 3.9, that is magnetic properties. Now magnetic property, the metal can have three properties, that is paramagnetism, diamagnetism and ferromagnetism. Now remember, magnetic property, okay, is a very important concept. Okay, many questions have been asked from here, very important. Now paramagnetism means what? Suppose you have kept a magnet, suppose this is a magnet, this is a metal, if the metal is getting attracted towards the magnet, we call it paramagnetism, okay, attraction towards the magnet. If you have kept the magnet, you have kept the metal, and the metal is repelling from the magnet, we call it diamagnetism. Now if we have the magnet, metal is there and it is very I can say strongly attracted towards the magnet, then we call it ferromagnetism, okay. Now, okay, this is the definition for this one. Now, so generally transition elements, so how to find, okay, how to find paramagnetism? So paramagnetism is present because of number of unpaired electrons. Okay, if unpaired electrons will be there, paramagnetism will be there. If unpaired electrons is not there, then the molecule will be diamagnetic, okay, or it will not have magnetism property, okay. Now there is something called as magnetic moment. How to calculate magnetic moment? So magnetic moment is the root mu is equal to root over of n into n plus 2. What is n here? N is the number of unpaired electrons. Okay, n is the number of unpaired electrons. Now the unit of magnetic moment is Bohr magneton. Okay, now the magnetic moment increases with the increase in the number of unpaired electrons. So if the number of unpaired electron increases, then the magnetic moment will also increase, okay. So let us do a question here. Titanium shows a maximum magnetic moment of 1, okay, one more trick I want to tell here. See, if the number of unpaired electron is 1, magnetic moment will be 1.7. Number of unpaired electron is 2, magnetic moment will be 2.7 or 2.8 something. 3, then 3.8. 4, it is 4.9. 5, it is 5.9. Okay, I think 2.8 this one, okay. Now this trick you can remember. If the magnetic number of unpaired electrons is 1, magnetic moment will be 1.7. If the number of unpaired electrons is 2, magnetic moment is 2.7 or 2.8. 3, 3.8, 4, 4.9, 5, 5.9, okay. Now we can do this question easily, okay. See, titanium shows maximum magnetic moment of 1.73 in its compound, okay. What is the oxidation state of titanium in that particular compound? So if it is showing a magnetic moment of 1.73, right, if the magnetic moment is 1.73, then what is the number of unpaired electrons? Number of electrons should be equal to 1, right. Now titanium electronic configuration, if you see, it is scandium titanium 3d2 4s2 but I want only one unpaired electron, right. So for one unpaired electron, how many electrons I have to remove? 2 electrons and 1 electron. So I need, if titanium is in +3 oxidation state, the electronic configuration will be 3d1, right. The electronic configuration will be 3d1 if titanium is in +3 oxidation state, right. So that is why, what is the oxidation state of titanium in that? If 3d1 is there, magnetic moment will be 1.73. So that is why titanium oxidation state in this compound is +3, okay. Fine. Now coming to next one, paramagnetism is not exhibited by. So if you know paramagnetism, it is by those elements which have no unpaired electrons. Sorry, it has unpaired electrons. If there is paramagnetism, there has unpaired electron, right. Now if you see copper, okay, the question is asking not exhibited by, right. That means it is paramagnetism is not there, means unpaired electron is not there, no unpaired electron. I wrote correctly first, okay. Now copper 2 plus, if you see CuSO4, here it is Cu plus 2, right. Cu plus 2 configuration is 3d9. By this time you should have remembered, and it has one unpaired electron. So that is why it will show paramagnetism. CuCl2 is again plus 2, right. So it will show paramagnetism. Copper I, Cu plus electronic configuration we have just seen, it is 3d10. There will not be any unpaired electron here, 3d10, no unpaired electron, then the molecule will not show paramagnetism. Correct answer for this question will be option number C, okay. Fine. Now coming to the smaller, we have almost like done the major topics. These are very small things, we can easily finish them. Formation of color compounds. So see, generally if you see the transition elements, you have seen chromium, this is bright orange in color, okay. Chromium, sorry, green in color, mercury orange in color, copper blue, nickel is almost black. So these what I say, transition elements are highly colorful compounds, okay. They are very bright and beautiful colors you can find in these transition elements. Now why these transition elements are so colorful? We have to understand the reason here. See, So there is, if you have studied atomic structure, there is electron, there is what we say, this is energy levels are there, right? So when these transition elements, electrons are there, when light falls on them, okay, what they do, they get excited, okay, and they generally absorbs the light in the visible region, okay. So they get excited, okay, and then after some time they come back to the ground state, okay. Sorry, one second. Okay, so after getting excited, they come back to the ground state, right? Now, when they come back to the ground state, they release some energy, okay, and this energy, or they release some wavelength of light which we can see, okay. So now what is the reason of this color for? That is your DD transition, okay. Now we will study in coordination chemistry in detail that when the d orbitals, the 5 d orbitals are there, they degenerate, okay, they form two levels are formed, and the electrons can easily get excited and can easily come down. So in this process we can see the color of the compound, okay. So see, when an electron from a lower energy d orbital is excited to a higher energy d orbital, the energy of excitation corresponds to the frequency of light absorbed. This frequency generally lies in the visible region. So now the color absorbed corresponds to the complementary color of the light absorbed. So whatever the light is absorbed, the complementary color of that will be visible to you. Now what is that? See, suppose so complementary color theory, if you know, we have like this. See, we have like this. So 6 boxes, V, B, G, Y, O and R, okay. So now if some color is absorbed is violet, it will be absorbed as yellow. If the light absorbed is blue, if the metal is accepting blue, it will be visible orange. If the metal is accepting green, it will be visible red. If the metal is accepting red, it will be visible green. So complementary colors are visible here, okay. Now the color corresponds to the frequency of the light absorbed is determined by the nature of the ligand. So this you will understand in coordination chemistry, which frequency of light will absorb, that depends on the ligands attached to the metals, okay. Fine. Now coming to a question. So what I can say, that if there is unpaired electron, okay, very important from where question will come, that point we have missed. First point is the color is due to DD transition. Second, for color, what is the must condition? There has to be unpaired electron, okay. If there is no unpaired electron, then there will be no color, okay. This is very important, okay. If unpaired electron is there, then color will be there. If no unpaired electron is there, then it will be colorless, okay. Now let us see, which of the following is colorless in water, okay. Let us see the electronic configurations. Titanium, scandium, titanium, 3d2, 4s2, right. Titanium 3 plus, 3 electrons will be removed, it is 3d1, right. So it has unpaired electrons, so it will be color. V3 plus, scandium, titanium, vanadium, 3d3 and 4s2. Vanadium 3 plus, if you take, 2 electrons will be removed, 1 electron will be removed from here, 3d2. It also has 2 unpaired electron, so that is why this one will also be colorful. Now chromium 3 plus, it is 3d5 and 4s1. Now chromium 3 plus will be what? 3 electrons you have to remove, 1 from here, 2 from here, it will be 3d3, right. That is this one. Now scandium 3 plus, scandium is scandium, titanium, vanadium, 3d1, 4s2, okay. Now scandium 3 plus is 2 electrons will be removed from here, 1 electron will be removed here, so we will get argon. So here you see there is no unpaired electron. If no unpaired electron, no DD transition, no color. The colorless compound is option number D, okay. Fine. Which of the following is green in color? Okay, so if you have remember, we will be studying about the color of the compound, okay. So manganate ion, MnO4 2 minus, okay, is green in color, okay, plus 6. So this is your plus 6 state, this is green in color. So the correct answer for this question is option number B, K2MnO4. Now coming to next one, Next property, that is 3.11, formation of complex compounds. Okay, so we'll study in detail the whole chapter. Coordination chemistry is about complex compounds, but these complex compounds are made up of transition elements. Okay, the p block, s block elements do not form transition elements. Who form transition elements? The d block elements. Okay, sorry, who form complex compounds? The d block elements. Now what is the here? So complex compounds are those in which the metal ions bind with a number of ions or neutral molecules, giving to complex species. Okay, so you can see some examples of complex compounds like this. This is transition metal, this is ligand, transition metal, ligand. Okay, transition metal, ligand, transition metal, ligand. Okay, we'll study about this in detail, so need not worry. Now the thing that you have to remember here is why the transition elements can form this complex compounds. Okay, so this is due to smaller size of the molecules. The metal ions are very small in size. Next, they have high ionic charges, and next they have the availability of d orbitals for bond formation. Okay, three factors you have to remember. Be very particular about this. Why they form complex ion? First, smaller size. Second, high ionic charge, and third, availability of d orbitals. Okay, 3 points remembered. Just note it down. We'll move to the next. Catalytic properties. So transition metals are and their compounds are known for their catalytic activity. Okay, so transition elements can also behave as catalyst. Now this is due to why they can have catalytic property? Because they have multiple oxidation states. Okay, and they can form complexes. Clear? Just now we discussed why they can form complexes. Because they can form complexes because they are small size, high ionic charge, availability of d orbital. Next, we are saying that transition elements can behave as catalyst. What's the reason for that? They can have multiple oxidation states and their ability to form complexes. Okay, next. Examples here, vanadium oxide is used in contact process, finely divided iron is used in Haber's process, nickel is used in the catalytic hydrogenation reaction. Okay, fine. Now let us do some question. Which one of the following characteristics of the transition metal is associated with higher catalytic activity? So just now we discussed multiple oxidation states and ability to form complexes, right? So you can say high enthalpy, no, paramagnetic, no, color, no, variable oxidation states. Okay, see how from just the theoretical part we can answer such questions, right? So very important, note down, make a proper short note of all these properties and learn it. Okay. Next, which one of the following characteristics? Okay, the same question is repeated here. Sorry. Okay, next one will go. Now coming to the second last property, that is interstitial compounds. Okay. Now interstitial compounds. So what do you mean by interstitial compounds? See here, you can see a small diagram that suppose these are the what I can say atoms. Okay, there is some space in between them, right? So when in between these space some atoms are trapped. Okay, that is these compounds are called as interstitial compounds. Okay, so why interstitial compounds are those compounds which are formed when small atoms like hydrogen, carbon, nitrogen are trapped inside the crystal lattice of metals. Okay, there will be some spaces, some vacant spaces are there, and inside this small atoms like carbon, hydrogen, nitrogen get inside and get trapped inside. We call it as interstitial compounds. Now they are usually non-stoichiometric and are neither typically ionic or covalent. Okay, so there is no ratio like to how many cations, how many anions, how many atoms should get trapped. There is no such ratio. It is just random. Okay. Now examples are there: TiC, Mn4n, Fe3H, VH0.56, TiH1.7. Okay, these are the different examples. Okay, now what is the benefit of these interstitial compounds? How do they help the metal? Suppose there is one metal and there is some metal with some interstitial sites are filled, then what properties are enhanced? So first of all, when these particles are coming in the interstitial sites, they have high melting points, okay, higher than those of pure metals. So if there is pure metal and now you put some hydrogen carbon atoms in between them, its melting point will increase. Okay, second one, they become very hard. Okay, then they retain the metal conductivity. So whatever the conductivity is there, it is still there, it is not affected in any way, and they are chemically inert. So these atoms which get inserted, they are chemically inert, they do not disturb the reactivity. The only thing they do is they make the metals more harder, more stronger, and they increase the melting point of the metals. Okay, fine. Now coming to a question here, many transition metals form interstitial compounds. Which of the following is not the characteristic of interstitial compounds? Okay, they have high melting point, yes, this is a characteristic. They are very hard, we have discussed, yes. They retain the metallic conductivity, yes. They are chemically more reactive than pure metals. No, just now we discussed that chemically they are inert. The correct answer for this question will be option number D. Okay, fine. Now, which one of the following elements form interstitial compounds? So, if you have seen example, let us go back to example. Fe can form interstitial compounds, right? So, the correct answer for this question will be option number A. Okay, fine. Now, coming to the last property, that is your alloy formation. Now, what is there in alloy formation? So, now see, because of similar radii and other characteristic of transition metals, alloys are readily formed by these metals. So, alloys means what? Mixture of metals. Many metals are mixed together. You can see the example here: steel, bronze, aluminium. Okay, these are the examples of alloys. Now, what is alloys? Mixture of metals. Now, transition elements can easily form alloys. Why? The reason you have to remember, that is because of similar radii. Okay, because of their similar radii, they can easily mix with each other and they can form alloys. Okay, now there is an example here. The alloys formed are hard and have often high melting point. So, why we need to form alloy? To improve the properties of the metals. Now, if you see, brass has copper and zinc. Example, bronze is made up of copper and tin. So, you see these all are copper, zinc, these all are your transition elements. Okay, fine. So, now we can go to the next here. Which of the following forms alloy? Okay, so which of the following forms alloy? So, we have just seen here iron and carbon. Okay, iron and carbon can form steel. I think we have written here something. Steel is there, right? So, steel is made up of, steel is made up of iron and carbon. So, which of the elements can form your alloys? So, that is Fe plus C. Okay. Next, which of the following is not a characteristic of the transition elements in the series from scandium to zinc? Scandium to zinc, this is not a property. The formation of colored ions, that is correct. Almost all the transition elements are colored. The presence of at least one unpaired electron in the d orbital, yes, there is also one unpaired electron. Next, the ability to form complex ions, yes, that is also correct. The possession of an oxidation state of +1, okay, what is not a characteristic. One second, which of the following is not a characteristic of transition elements in the series from scandium to zinc? Okay, scandium to zinc, if we are going, okay, the possession of an oxidation state of +1. So, if you see, scandium has an oxidation state of +3, right? So, if you go from scandium to zinc, there is no +1 oxidation state for scandium, right? The correct answer for this question will be option number D. Okay, fine. Now, let us practice some previous year questions. Okay, first one, a transition metal exists in the highest oxidation state. It is expected to behave as. So, this is just now we discussed, when the metal is in the higher oxidation state, it has acidic character. Okay, so remember, it will behave. Okay, see, if metal is in the higher oxidation state, very high oxidation state, +7 suppose. Now, what it can undergo? Can it, suppose manganese, can it undergo further oxidation? No. Why? Because it is already in the +7 oxidation state, right? In that case, what will manganese do? Manganese can get converted to Mn+2 only, or some other Mn+4 or Mn+6, right? So, what is manganese undergoing? If it is already in the higher oxidation state, it will come to lower oxidation state and it will behave as, it will undergo reduction. If it is undergoing reduction, then it will behave as an oxidizing agent. Okay, the correct answer for this question is option number A. When a metal is in the higher oxidation state, further I cannot undergo oxidation, right? It can only come back, it can undergo reduction. If it is undergoing reduction, then we call that it is an oxidizing agent. Okay, next question. What will be the value of X in Fe X plus if the magnetic moment is 2.4? Okay, sorry, this is root over of 24. Okay, root over of 24. Now, if you see, mu is equal to root over of 24. So, if I write, the mu formula is n into n+2, right? So I can write it as n is equal to 4 here, right? That means the number of unpaired electrons is 4. Now if you remember my Fe electronic configuration, what is the electronic configuration of Fe? 3d6 and 4s2. This is 1 2 3 4 5, so 1 2 3 4 5 and 6, so 3d6 and we have 4s2 here, right? So now what happens, there has to be 4 unpaired electron. When we will get 4 unpaired electron, if these 2 electrons go out, then the configuration will be 3d6 and we can get 4 unpaired electron. So what should be the oxidation state of Fe here? +2, right? In Fe in +2 oxidation state, we will get 4 unpaired electrons, right? Okay, next question. All copper 2 halides are known except iodide. We have discussed this in very detail, the reason for that. So they are telling that we cannot get copper I2. What is the reason? Copper 2 plus oxidizes iodide to iodine, right? Very much time we took and discussed that. Yes, next question. Which of the following pairs have both the ions colored in the aqueous solution? Both the ions are colored. So for colored, what is the condition? There should be unpaired electron, right? There should be unpaired electron. So now if you see, scandium 3 plus have no unpaired electron, so we can eliminate this one. Titanium 4 plus has no unpaired electron, so we can remove this one. Copper plus has no unpaired electron, so we can remove this option. Mn2 plus has unpaired electron. Ti3 plus has also scandium, titanium. Sorry, one second. Titanium, scandium. Titanium is 4s2 and 3d2, right? Yeah. So Ti3 plus has 1 unpaired electron. So this is also having unpaired electron. This is also having unpaired electron. So both of them will be colored. The correct answer for this question will be option number D. Okay. So last question here. Mn2 plus compounds are more stable than Fe2 plus compounds towards oxidation to their +3 state because. Okay. So now if you see, Mn plus 2 is there and Fe plus 2 is there, right? Now they are saying that Mn plus 2 is more stable towards oxo. So Mn2 plus doesn't undergo Mn3 plus. Now the reason for this, you know, it is D5 configuration, stable D5 configuration. So Mn2 plus is more stable with third high ionization energy. Okay, it is very stable because of D5 configuration. Okay. So yes, so this is a homework question for you. Which of the following statements are correct about zinc, cadmium and mercury? Okay. So read this all the questions and try to answer this question in the comment section. Okay. So yes, students, we have covered a very important, very major topic of D block, and I personally feel very difficult to read this particular chapter from the NCERT book because it is given in such a I feel it is not more, it can be more arranged way. So I have tried my level best to make it simplified, to make it arranged, and have taken only those points from where the questions are being asked. Okay. So please make sure that you make proper notes from this chapter, from this particular section. Okay, and then you revise it regularly and then try to attempt the questions. You will definitely be able to do it. Okay. So yes, now thank you for watching this video, and please subscribe the channel if you are enjoying learning with if you are enjoying this series, if you are learning with me every day, then please subscribe the channel so that you can know about the new videos that we are going to make. And also remember one thing, join our WhatsApp channel so that you can get everything, the notes, the question papers, solutions, everything will be provided in the WhatsApp channel. Okay. So yes, next we are going to start with important compounds, potassium permanganate and K2Cr2O7 reactions, and many things we are going to learn. So yes, let's see in the next class. Okay. So please study hard, keep smiling, stay healthy. Okay. Thank you. See you soon.